All right. Welcome, AP Chemistry, to our first set of notes for Chapter 13. This is Chemical Kinetics. Just kind of fair warning, a lot of math in this chapter. It's a little tough, but bear with me, and we'll get through just as much as we possibly can. So here it is, Chemical Kinetics. Thermodynamics. We're looking at thermodynamics calculations in chemistry. We're generally answering questions like, does a reaction take place? Is it energetically favorable? How much heat's being released with delta H? How's disorder changing with delta S? Or maybe even Gibbs free energy for delta G. And kinetics is a different branch, as how fast will a reaction proceed. That's what we're going to work with this chapter. So we talk about rate a lot. Reaction rate in this chapter is the change in the concentration of a reactant or a product with time. And I think as we work through our first couple of rate equations, I think that's going to make a lot of sense. It's measured in molarity per second. And so here we have just something very simple, A turning into B. And so our rate of our chemical reaction is equal to the negative change in concentration of a reactant over time. That's the rate. The reason it's negative is because if a reaction is proceeding to the right, the A is being consumed. So that's why it's negative. We're losing that compound. So our delta A is change in the concentration of A over a time period. Now we've also got another rate for B, for our product, and that rate is the change in concentration of the product, B, over T, but you'll note that this one's not negative, because this, being on the product side, is being formed, and so its rate is going to be positive, because we're getting more of this molecule B. And then its definition is really just the same as A. So then here we have, because A decreases with time, delta A is negative. So hopefully not too bad. So we have A changing into B. Kind of get this image of a clock. I guess we'll go through those. It's kind of nice. We start off with all A is red, or black rather. And then as the reaction proceeds, we get a little more turning into red and less black, and more red and less black, until we get to the end of the reaction where we have mostly red and only a few black scattered in there. And so what we're trying to figure out with rate questions is, how fast is this occurring? Here they've got this little watch hand going around kind of thing. And so here's our graph for B molecules increasing in number, while A molecules decrease in number. And so we'd like to say that the rate that A molecules are being consumed is very likely going to be equal to the rate that B molecules are being formed. So if we say that, we can actually set these two equal to one another, and that's where we're going to take something like this and make it kind of useful. So here we have an equation set up, bromine, HCOOH, what would that be? Methanoic acid, something like that. Gives us bromine, hydrogens, and carbon dioxide gas. So bromine here, aqueous bromine, is kind of this red-brown color. And here it is over time reacting. And we can see as it reacts, it becomes lighter and lighter in color until it's very nearly clear. And so this gives us the idea that our concentration of bromine is going to be about equal to our change in absorption. So our concentration change is equal to our absorption change. And we get a graph that's something like this. Time 1 is a little less than time 2 is a little less than time 3. And their absorption, of course, is changing as well as this reaction proceeds. So we'll look at another graph of this. This might be a little better. This is the rate at Br2 being lost, so the rate of consumption of this reactant. And here you have it numerically as well, time in 50-second increments, and then the concentration in molarity. And you can see that it's not truly a perfectly straight line. It does have a little bit of a slope. But at any given point, we can kind of pick two concentrations and find a rate based on those two concentrations. And so what we'll end up doing when we do problems like this in a calculation is we're going to take an average rate, kind of a best fit line. It's not going to be exactly, it'll be an average. And we'll use those in our equations. So that's kind of nice. Just be aware that what you're getting for these problems is an average. It's not necessarily an instantaneous rate from a teeny tiny sample in some beaker somewhere. It doesn't really work that way. But an instantaneous rate would be a specific instance in time if we could just measure this point rate right here at 2 times 10 to the negative fifth. That's an instantaneous rate. Whereas the average rate of this whole reaction is probably not quite 2.09. So they're just letting us know here they get their rate from the slope of their tangent of these triangles, which is our change in concentration and time, which make up the y and x-axis respectively. So here's something pretty similar actually. Time, bromine again, its concentration, our rate and how that's changing, and then our K, which is our constant. And you'll note the cool thing about a constant is, well, it should be constant. And here you can see that while our rate is changing and our bromine is changing, our constant is just solid. 3.5 times 10 to the negative 3. 495, 515, 50, 52, 48, 51. I mean, that constant, it's beautiful. It's 3.5 times 10 to the negative 3. It's constant. That's what a constant's supposed to be. And once we find those, then we can really work with any concentration of anything in our equation because they'll all be changing with respect to the constant. So when you're given a problem like this, K is a very valuable thing to try to find. So that's something to keep in mind. So here now we flip that graph from the loss of bromine concentration to the bromine concentration and how it affects our rate. So our rate is equal to the constant multiplied by bromine. And here you could rearrange that to solve for K, which is fine. And K is our rate constant. And here we said, 3.5 times 10 to the negative third. So here's another reaction. Looks like we have hydrogen peroxide decomposing to water and oxygen. And this graph's going to be a little bit trickier, but they're measuring a change in pressure over time. As that hydrogen peroxide decomposes, it releases oxygen gas, and the more oxygen gas that it releases, the more pressure that we have. So we're going to do a little deriving of some equations here, but we start with the ideal gas, PV equals nRT. We rearrange it to solve for P, and then we say, okay, N over V, that's moles over volume. Moles over volume is like moles over liters, which is molarity. So we go ahead and take that out and we put in concentration. So pressure is equal to concentration of oxygen times the universal gas constant times the absolute temperature in Kelvin. So our oxygen concentration is equal to, we're just solving here with these two parts of the equation, solving for O2, is 1 over RT multiplied by our pressure. So then we can say that our rate is equal to our concentration of oxygen gas divided by our change in time, and that is equal to what we solved for earlier, which is 1 over RT times our pressure change over time. So we're just applying this over a change in time. Here we've got a different diagram of the same reaction. H2O2 up here, hydrogen peroxide, decomposing, water, and oxygen gas. Here's the slope of the line. Kind of having to take an average again because as you can see it's a little bit of an arc. But if we take that best fit line, which is this red triangle, we get 0.12 millimeters of mercury a minute. So we can use that. So let's look at stoichiometry. Here we've been using stoichiometry a lot. 2 moles of A are consumed to form a single mole of B. And we're going to go ahead and take that coefficient and put it as 1 over the coefficient, the concentration of A over time. Now for B, if you really wanted to, you could write that it's 1 over 1, but that would be kind of pointless to write, so we just leave that out and say it's delta B over delta T. So then we can write, if we had coefficients in front of each of these, then we could say that our rate is equal to, don't forget your negative signs with your reactants, 1 over little a multiplied by the concentration change in A over T, which is equal to the negative, same thing here, which is equal to the positive, same thing here, which is equal to the positive, same thing here. And so if we set each reactant equal to each product, if we have to solve from one to the other, we can only use the two that we're concerned with. We don't have to use all four. It's kind of convenient. So practice writing the rate expression for the following reaction. Might be a good idea to go ahead and pause the video and see if you can do it. Just try try just our reactants and see if you can do it. Just rate equals. All right, well, hopefully you paused the video and gave it a try. And hopefully you found something that looks like this. Rate equals negative methane over time, and there's no values in front of there. And that's equal to negative 1/2 oxygen over time. Our 2 is where we got the 1/2, which is equal to a positive carbon dioxide over time, which is equal to a positive 1/2 water over time. So our rate law is going to express the relationship of the rate of a reaction to the rate constant, K, that we mentioned earlier, and the concentrations of the reactants raised to some powers. So this is the part that gets a little tricky. Our rate is equal to our constant times our concentration of A and B to the xth and yth power. Those x and y actually have nothing to do with this A or this little b. So we can say that the reaction is the xth order for A and the yth order in B. It's a bit of a tongue twister. Like so many things in chemistry, during the notes part, it doesn't really make a whole lot of sense. Once you do a couple problems, it sort of starts to work out. So if you want to find the overall order of the reaction, you add your x and your y together, and you get the overall order of the reaction. So let's look at one example of how you could do that. Here we've got a reaction where we have a fluorine gas reacting with ClO2 to make fluorine ClO2. And here we can look at this table, and it's a data of rates. So here's our initial rates, and we can look at how they're changing. We can look at how we're changing concentrations of fluorine and chloride. And from those informations, we can figure out what order our reaction is with respect to fluorine or respect to what I think is chloride. I hope it's chloride. Might be like perchloride or something. Maybe I'm messing that up, but here we have it. So our rate is equal to a constant times the fluorine concentration raised to the x times ClO2 raised to the y. We just have to figure out what x and y are. So we look at these things and we say, okay, what if we take our chloride and we keep its concentration the same and we double fluorine's? Our rate of our reaction doubles. So the relationship between the concentration of fluorine change and the reaction rate change is exactly a 1-to-1. So if we double our fluorine, the rate doubles. That means that x equals 1. So fluorine is raised to the first power. It is directly proportional to its change in concentration. Rather, to the change in the rate from its change in concentration. So let's look at the next example. Here, we take fluorine and we don't change its concentration, but we change ClO2's concentration. We make it 4 times higher, and our rate speeds up by 4 times. So ClO2 is actually the same as fluorine. If we quadruple ClO2, we quadruple the rate. So y is equal to 1. It's raised to the first power. So it's kind of like saying our rate is dependent upon the concentration of fluorine, linearly, just directly, and the concentration of ClO2. And so now we can write our rate law, which is K equals F2 ClO2. And there's no squareds or cubed or anything like that because they're all in the first power. So rate laws, we always have to determine these experimentally. You have to get a chart of values and we have to figure this out. Reaction order is always defined in terms of our reactants, not the products. The order of a reaction is not related to stoichiometric coefficients of the reactants in the balanced chemical equation. And so here we looked at the reaction that we were just looking at on the last slide, fluorine, ClO2, fluorine, ClO2. And our rate is dependent only upon how much fluorine I have, how much Cl2 I have, not on how much product I have. And then they're just pointing out here that that 2 really has no bearing on any of this stuff. It does not belong here. No, that's X and Y order, not anything to do with the coefficient. So here's an example of determining the rate law and calculating a rate constant. So we've got to figure out a rate constant, which is K, from our following reaction. So we've got S2O8, we got 3 iodines, we're making sulfate, we're making iodine. And so here's what we're looking at. Experimental trials. We've got S2O8, iodine, and rate. So you can look at this and say, okay, let's do what we did last time. We keep S2O8 concentrations the same. We cut iodine in half. We cut the speed of our reaction in half. So hopefully you know that I is raised to what power? The first order, right? You say, okay, we take iodine, we cut it in half. We take S2O8, we cut it in half. I don't want to do that. That might get a little too confusing. What if we keep iodine the same? There, that's better. Let's keep iodine the same. And let's double S2O8. Yeah, I like that a lot better. Our reaction rate doubles. So we say, hey, same boat. What order is S2O8? First order again. So this is nice. A little repetitive, but it's nice. So here's our rate. We figured out X and Y. You double the iodine, the rate doubles. You double S2O8, the rate doubles. So we're set. We're in the same boat we were in the last experiment. We just found the rate constant. So now we got to find K. K is actually really easy to find because it's rate divided by the concentration of our 2 reactants. And pick your experiment, whichever one you want. Pick number 1 or 2 or 3. You're going to have a rate. You're going to have a concentration of 1 reactant, concentration of 1 reactant. You just divide them. That's it. So here it looks like they picked their first experiment. Why not? 2.2 times 10 to the negative 4th is our rate. Concentration of S2O8 is down here. Concentration of iodine is down here. Just real simple math gives us 0.08 per molarity seconds. Or molar seconds, if that's the way you would say that. So we found a K. And once we found a K, we can solve for whatever we need to solve for, really. So I think that's going to be about enough to get you started on some of your calculations for this chapter. This is first order reactions here, showing that if A is going to the product and the rate is dependent only on A, then your first order reaction would be rate is equal to K multiplied by the concentration of A. So with these first order reactions, you can solve for them just like we did the last problem, where you put rate divided by the concentration of A. It's going to give you units of seconds to the negative 1. And then here you can see for our first order reactants, as time goes on, the concentration of A decreases. And then if you make that graph a natural logarithm graph, it's more of a straight line, and our slope is equal to negative K. So our slope is equal to our rate constant. But that's enough to get you started for Chapter 13 calculations. I know it seems like a lot at first. It is a little confusing, but I assure you the more we practice with it, it does become a little more clear as far as clarity can get, at any rate, in AP Chem. So thanks for your time.